What we're going to do in this second part of this session, we heard about the options and the plans for brown coal generation, but also CCS before lunch. And now we're looking at options for other sources of energy within the Victorian energy mix. And unfortunately, one of our participants, Warwick Johnston, has called in sick and won't be able to make it. But we do have three, and then we'll use that extra time in discussion. So have plenty of questions. So it's great pleasure to introduce Rachel Watson, who is the General Manager Australia of Pacific Hydro, with responsibility for the company's Australian renewable energy project development pipeline, construction, operating assets and commercial team. She's been a Director of the Clean Energy Council since 2014 and chairs the CEC board. Rachel Watson.
Thank you very much, Snow, and thank you very much for having me today. This is not the usual forum of industry participants that I get to speak to. Perish the thought that I might have brought with me a lump of coal today, but if I had brought a lump of coal and I was to just throw it out there, I have a feeling it would strike somebody with a PhD. So I was asked to address some deceptively simple questions today, PhDs notwithstanding, and so I've taken a fairly fundamental approach to answering those questions. So perhaps if we consider this a sort of scene-setting presentation, subsequent panellists will be able to dazzle you with their very well analysed graphs and statistics, and I was particularly relying on Warwick to produce some of those. He's a fellow board member at the CEC, so I'm disappointed that he's not here to do that. So Pacific Hydro, probably well known to some of you, we're a Victorian renewable energy company, and we built Victoria's first wind farm and Australia's first commercially operated wind farm, which is the little Codrington wind farm down near Port Fairy in Western Victoria. And Codrington makes an appearance in my presentation a little bit later on. So we've really been on the very long journey of how do you make wind farms commercially work in the state of Victoria since the very beginning of the industry here. So what I'm really going to address today is some, as I said, some pretty basic questions in the context of the Victorian wind industry. So where is it? Where is the resource? Where are we headed in terms of scale? What does it cost? I've got my own view on that. We've seen quite a few slides already on the LCOE of wind versus other technologies. And then what does it actually look like? So Google Maps helpfully produced this little graphic of wind farms in Victoria. And the first thing that you really notice is the concentration of the wind resource. In fact, if you were to put up a map showing where the coal resource was in Victoria, it's almost the inverse of this map. So very much concentrated in Western Victoria, down along the coast and then up through the Western Plains. So according to the key, the blue are the operating wind farms, orange are projects in planning or under feasibility study, and the green have planning approval. So I think that this map's probably out of date. Almost every day, every week, we're seeing announcements of new wind farms. And there was a major one in the paper this morning, which I will come back to a little bit later on. So in the NEM, in August 2017, so last month, according to Green Energy Markets, renewable energy was about 20% of NEM's generation, which included rooftop solar. And if you took out rooftop solar, that's 17.8%. And about 7 of that 20% came from wind, and about a third of that was generated in Victoria. So between Victoria and South Australia, they really have sort of the lion's share of the wind resource in Australia. I was interested, Tony, to hear you talking about better transmission, both intrastate and interstate. If you look at the transmission network I wasn't clever enough to overlay that map on top of this one. But we think about where all the major transmission infrastructure is in Victoria, it very much connects the Latrobe Valley with the very large load centres around the state. So we have a big wind farm at Portland, and in fact we connect that wind farm into the Alcoa Smelters switchyard, so we actually sit behind their meter, and they are connected into the 550 kV transmission line. And as you drive out of that switchyard, to the left you'll see some beautiful sculptural wind turbines on the capes down to the ocean, and to the right, heading back to Melbourne to the east, you see a long line of 550 kV power line pylons marching their way in pretty much a straight line without fear or favour right across the state back to the Latrobe Valley. Now that infrastructure, as I understand it, was all established in the 60s and 70s, and of course it's clearly following where the load is as well as where the resource is. The issue we've got with transmission in Victoria at the moment is if you're talking about where this new resource is, it's very much concentrated in Western Victoria, and the solar resource follows a similar pattern. East of the divide and the further north of the state you can go, west of the divide and the further north you go, and you're up into territory which has very, very skinny transmission. So one of the real keys to unlocking renewable resource in Victoria is going to be upgrading that transmission system. And one of the things that we're trying to amp up our advocacy on in respect of the Victorian renewable energy target is making sure that it comes along with some upgrades to transmission system. As I understand it, the regulatory investment test for transmission, the RIT-T, is very much focused on where demand lies. So in the past, the justification for transmission upgrades has been based on where the customers or the users of energy are. They're not in Western Victoria. So this is going to be a big challenge for us to try and flip around that regulatory investment justification to where the resource is so that we can move the energy from the resource to the load. I was also, as I said before, really fascinated to see in the Fin review this morning that West Wind Energy, the developers of the existing Lal wind farm development, have announced their application to develop Australia's largest wind farm, the Golden Plains wind farm, which will also be right in the middle of that cluster, somewhere just a bit south of Ballarat. 231 3.5 megawatt turbines. They're the biggest turbines that we're seeing in the state at the moment. So we'll come back to that in a second. So in Victoria, this is data from the Department of Energy and the Environment here in Victoria. So we have nearly 1.5 gigawatts of capacity in the major wind farms, so those over I think it's over 5 megawatts, that metric. But then another almost double that of approved wind farms, not yet in operation, 18 megawatts worth of applications lodged, although I think that's probably changed today with the announcement of the Golden Plains one, and 191 megawatts under construction. So you can see the move that we're planning to engineer here from about 1.5 gigawatts to more like 4.5 gigawatts. And this is going to be underpinned basically by the Victorian renewable energy target. So that legislation gets through, then the intention is to run a request for proposal for up to 650 megawatts of renewable energy generation. So 550 large-scale technology neutral, it's likely to be wind, and a further 100 specifically reserved for large-scale solar generation. So clearly the target of the current government is 25% of Victoria's energy by 2020, scaling up to 40% by 2025 to come from renewable sources. So cost estimates, everyone's had their say on this, I think, today. I'm fascinated by this topic because the rate of the cost curve reduction, like solar, has taken everyone by surprise in wind, and this is now being driven very much by the transition of offshore wind turbine technology, where they're building very, very large turbines and transferring that technology into onshore wind turbines. I nicked these graphs from AI Group. I'm glad Ines isn't here. So you can see the NEM average, the NEM future, I think they're the same red bars that Innes had on his graph, and wind sitting there at the same level as the NEM future. You can see on the right-hand side of the slide how costs have come down since 2005, with solar thermal at the top in the red and solar PV in the yellow and wind there in the mix. So Origin's recent results presentation showed that their bundled cost of power purchase agreement prices from 2012, where it was between $120 and $140 a megawatt hour, has now moved to something between $60 and $80 a megawatt hour. Now that Golden Plains wind farm that I mentioned today, I'm taking this from this morning's Fin Review article, they have said they have built their economic model for their wind farm on the basis of power prices alone. And one of the earlier speakers, might have been you, Tony, mentioned a long-run average of about $60 a megawatt hour. So that actually is very consistent with the prices that Origin is talking about in their results presentation. So the changing shape of wind farms, I apologise for the rather crude nature of my little graphic here, but I wanted to try and illustrate the scale change that we're undergoing in terms of how we're building wind farms. And thanks to Rosemary for reminding us it's grand final weekend. That middle bar is the height of an MCG light tower, 85 metres. The Codrington wind farm, which was our first wind farm, it's only 14 turbines, 1.3 megawatt turbines. They're 79 metres to the top of the tip. Stockyard Hill, which until this morning's announcement of Golden Plains was to be the largest wind farm in Australia, 149 3.5 metre turbines. They're going to be more than twice the height of the MCG light towers. So this has significant implications, I think, that we haven't really understood or dealt with potentially in the industry yet. So if you compare Codrington with Stockyard Hill, 10 times the number of turbines, the turbines are more than twice the height. So in terms of community engagement, visual impact, I think this is yet to really be fully realised and is probably one of the next challenges facing the wind industry. However, the increasing size of turbines, coupled with the fact that we've got early sites like Codrington, which will in the next 5 to 10 years start coming to the end of their useful life, means we've still got considerable resource we can access because we can repower those sites with far more efficient turbines. And that's going to produce a really interesting state of affairs. Thank you very much.
Just to remind you that there's an extensive panel in this, and then there'll be a chance to ask some questions of Rachel. The next speaker is Dr. Keith Lovegrove, who's the Managing Director of ITP Thermal. He's also managing the solar thermal for the ITP Energised Group and Managing Director of ITP. But Keith also actually is currently a member of the University of Adelaide Centre for Energy Technology Advisory Board and serves on the Australian Renewable Energy Agency's advisory panel and is a board member of Australian Solar Thermal Energy Association. Keith.
Okay. Whoops. Too aggressive on the button there. Okay, good afternoon everyone. So concentrating solar thermal, most of what I'm going to tell you about here I think is really a national or global perspective, but I've got at least one slide that mentions Victoria to do it justice. So concentrating solar power, I think everyone's aware of it now, particularly with the talk of the Solar Flagships project in Port Augusta, and that's the second from the left, the configuration of the tower surrounded by mirrors. On the far left there you see a trough concentrator, and most of the world's installed capacity in solar thermal is the trough concentrators, but there's a general consensus now that it's the towers and heliostats that at least have the focus of attention, shall we say, at the moment, and then there's other configurations as well. If you look at the map down there of global CST capacity, you'll see that it's at about 5 gigawatts at the moment, so it's only, let's say, 2% of where PV is in the world. In fact, if you look at the history of the various technologies you can see that the growth trajectory of PV is about a decade behind the growth trajectory of wind, and then CSP is about a decade behind, but with a very similar trajectory again. So these things can come. So you can see there that Spain played a very big role in kicking off the industry, and they managed to put out over 2 gigawatts of installed capacity in about 7 years. And that was simply based on setting a feed-in tariff that was sufficient to finance these plants. So it's clearly the case that if the policy settings are in place or the income source is guaranteed, that it is quite possible to build these things quite fast. And then Spain just completely reversed its position after a change of government and had their version of Tony Abbott or whatever it was. We see that the USA has been consistently on and off over a very long period, and what you see there is its individual ad hoc initiatives from states, actually. Certain amount of help from the DOE federally with loan guarantees at some point, but it's really the yellow curve that's the one to watch. And I was in China just about 3 weeks ago and I saw a 10 megawatt molten salt tower plant right there running, and that was just a pilot done by a company that was halfway through building a 100 megawatt plant in the same configuration. There's 3 big plants under construction in China, another 5 that have done the first sort of site works and appear to be going ahead. So they're really moving ahead there. What does it look like? Here's 2 iconic plants, both in the USA, but as I say, we can increasingly look to other countries for where it's coming from. The one down in the bottom right there is the Crescent Dunes plant in Nevada. It's the solar reserve plant that they're essentially talking about replicating in Port Augusta, but slightly reconfigured. Interestingly, reconfigured more as a peaking plant than the original configuration in Nevada. The trough plants, where have they got to? The Solana plant, Abengoa Solana plant in Arizona, is the biggest single trough plant so far, 280 megawatts with 6 hours storage. The Crescent Dunes plant in Nevada has 10 hours of storage. One of the reasons that the tower plants are favoured is that the salt tanks are running at a hotter temperature in a tower, so you get more energy into the same tank. I'll talk about that more in a second, right now in fact. So this idea of concentrating solar thermal has energy storage built in. This is its competitive advantage. We can argue about the LCOE, and I'll have a slide about that in a minute, but it clearly is more expensive than wind and PV as variable sources of energy. So its value is the fact that for that LCOE you get energy storage built in. There's this concept of 2-tank molten salt, which is now standard. Virtually all new plants around the world are using this, be they trough plants or tower plants. A higher temperature difference makes it cheaper because as you move this liquid from the euphemistically called cold tank at 250 degrees to the hotter tank at nearly 600 degrees, the bigger that temperature difference is, the more energy you've stored. The salt never wears out. It's not table salt. It should be called molten fertiliser. It's a mixture of sodium nitrate and potassium nitrates, always kept as a liquid, so it's not a phase change, just a hot liquid. Never wears out. You can sell it at the end of its life. The life should be at least 30 years. And a really important point when you're configuring a plant like this is that adding storage actually lowers the LCOE. These plants will have a lowest LCOE at probably around 10 to 15 hours of thermal storage. Why might that be? It's because you have a heliostat field, it's focusing onto a receiver, you've built yourself a power block. If you don't have storage, you're going to tend to oversize that field for midday in summer and waste a lot of that energy, but that's the price you pay for keeping your turbine going more of the time. As soon as you add storage, there's less of that energy going to waste. Hence, this interesting situation that the lowest LCOE comes with 10 or 15 hours of storage. Now, interestingly, that may not be the best thing to build because maybe we want more of a peaking type configuration with the same tower, the same heliostat field, the same stored energy, but a bigger turbine so you can pump it out more in that peak period. Here it is, the slide that mentions Victoria. And the main point to make here is that we don't tend to think of Victoria as the sunniest state. There's no doubt about it. Alice Springs is sunnier, the Pilbara is sunnier. We don't want to build solar in the Latrobe Valley, I'm afraid, but northern Victoria, and there's an awful lot of northern Victoria, is absolutely on par with what the rest of the world considers very sunny places. So, more than half of the world's solar thermal plants are built in southern Spain. Seville is the best of southern Spain. Seville has about the same direct beam radiation annual resource as Mildura. So that's where we are. We're a bit less than Nevada, where the Crescent Dunes plant is, but note also, interestingly, that it's pretty much on par with Port Augusta. So Port Augusta is not the sunniest part of South Australia. Olympic Dam would be better, but the fates are aligned and people have chosen Port Augusta, and it's a very, very respectable solar resource indeed, as is Mildura. So there's no shortage of land. The biggest issue, I suppose, around northern Victoria, as Rachel pointed out, the transmission connections there are a bit weak. Though interestingly, when you build your first few plants with storage in those areas that are a bit weak for transmission, what you actually do is help the situation out there and actually sort of strengthen up the network out there. But at some point, we have to think about larger transmissions. Now, the things to know about CSP when we're talking about reliability and security and everything that's focusing people's minds at the moment. So it's synchronous generators with steam turbines. It's what everyone's used to. It gives you that inertia. The CSP steam turbines are customised for more agile, faster starting, faster ramping. But certainly it's not as fast as open cycle gas, and certainly not as fast as a battery, but a lot faster than a coal plant traditionally. Same inertia characteristics as coal or gas. Very key point that if you've built this thing and you've got these tanks, and people are now talking about security reservations, so to speak, if one was to ask the developer of a CSP plant, could you please add an extra 10% of energy storage and we will contract you to never discharge that, then that's a technology option, and the marginal cost of adding an hour of storage is really quite low indeed. There's also a rather surprising thing, which is that you can, if you wish, electrically heat the molten salt. It wouldn't give you a very good round-trip efficiency, about 40%. It becomes the cycle efficiency of the turbine, really. But if people have started to create a situation where the wholesale price of electricity is going to zero or negative, then hey, that would be a very, very cost-effective way of sucking it up with a resistor in the tank. Now, the cost is a very tricky thing. It's not simple. Depends how you configure it. But things to know are that there is a sweet spot at about 100 megawatts, and you probably don't want to go below 50 megawatts, and it's because steam turbines are less efficient in small sizes. That's the number one thing to know. But you can configure different amounts of storage, different sizes of turbines, depending on whether you want peaking or intermediate type behaviour. But the really interesting thing about cost is the extent to which it has come down. ITP did this study back in 2012, and we thought $250 a megawatt hour then. We did quite a detailed bit of work in 2015, which isn't very well known, but we did it for Abengoa and concluded it had dropped to about 170 then. And we would say, if you examine the capital cost announced for the Solar Reserve project, forget about all this talk of $78 a megawatt hour, that's smoke and mirrors. The capital cost and the announced amount of generating energy, 490, I think, gigawatt hours a year, that seems to come to around $150 a megawatt hour as an LCOE, and I think that's a pretty fair estimate. What it says to us is that the downward trajectory is the very best that we thought back in 2012 that it might follow. So I think that's actually fairly good performance. But of course, that's considerably higher than the $60 or $80 for wind, etc. So why do you bother? Well, you get a time of day benefit, 2 minutes, which depending on how you look at the market signals, is of the order of 100%. If you could sell your energy at the times in the wholesale market where it's most valuable, that is therefore 100% more valuable than the NEM average. You get the ancillary services benefit. They're getting a lot of media attention at the moment, arguably because we've neglected them somewhat. I think in the long run we'll find it's actually fairly easy to provide our security services and FCAS and whatnot. The network benefits are very interesting because if you build a plant with firm capacity in a place where the network's weak, you can actually avoid sometimes some transmission expense that's equal to the whole value of the plant. Can argue about the potential for creating local jobs and the fact, and in that regard, studies in Spain showed that with this kind of technology, it's much more about people welding steel and digging holes and pouring concrete in, so you tend to keep more of the value in the local region, in the state, in the nation, as distinct from in a shipping container from China. Okay, value propositions must be optimised on a case-by-case basis. Few challenges. Number one is that so far all our renewable policy, be it state-based or the RET, has rewarded every megawatt hour equally. And I think, you know, in the last few months with the Finkel review, and everyone now realises that not all megawatt hours are equal, and that's the fundamental thing. The problem we have now is, well, what do we do about that? What do we set in place to manage that situation? Australia has a lack of familiarity that we just simply don't have one here that the journalists can go and visit. So somehow the fact that there's 100 of the things around the world doesn't seem to matter. No one quite believes that maybe the Coriolis effect is going to make them fall over or something, I don't know. So there's also a misunderstanding of the need for the greater than 50 megawatt scale. I mean, there's an interesting thing that people want to build little batteries and little things to bring their way up to it, but here we are talking about post-Hazelwood, so we have to build 16 versions of Crescent Dunes to replace Hazelwood capacity for capacity. So to build in a module of 100 megawatts, I put it to you, is actually a very small modular approach. Yet somehow, you know, funding agencies and so forth, they say, oh, 50 megawatts, somehow it's too big. Well, no, actually it's really quite small and modular, and that's how we should think. We've had some bad history. Solar flagships was a complete failure in terms of getting solar thermal up in Australia, and there's obvious reasons for that in retrospect. There is a sort of naive belief in some quarters that maybe it's easy, so we should do everything from scratch in Australia, but no, I would argue it's a global industry. We don't try and make our wind turbines from scratch or our PV panels. So in conclusion, it's growing strongly, a decade behind PV, high value dispatchable renewable electricity generation, bigger position in the value chain. We need to crack on, and it looks like we are with Solar Reserve, but bear in mind that there's a lot of water to flow under the bridge. They've got an offtake agreement. They haven't got financial close yet. But most importantly, I think our energy policy has got to start rewarding the extra values in the renewable energy space or the zero emissions space with extra value, which it hasn't done yet. So I would argue that we could put multipliers in a clean energy target. I mean, we're talking about an emissions multiplier in a clean energy target. I don't see why we can't have a time of day multiplier also to bring on these things. And if people are following the market signals like that, I would argue that most of the things like inertia and FCAS type services will just kind of come naturally from people following the value of the energy. I think we could consider maybe a parallel zero emissions ancillaries market also, so that everything goes in proportion. Okay, thanks very much.
Thanks, Keith. We'll bring you back for the panel in a moment. The third speaker in this session is Dr. Barrie May. Barrie has more than 20 years' experience in leading projects at CSIRO and as a private consultant in sustainable biomass production and carbon sequestration. Recently, though, he completed a survey of waste biomass production from municipal, commercial, industrial, including forestry and agriculture in Victoria for Sustainability Victoria and the Rural Industries R&D Corporation. Welcome, Barrie, wherever he is. Ah, here he is.
Thanks for that intro, Snow, and thanks for the opportunity to come talk about biomass at this great symposium. So firstly, I guess biomass is a bit like the forgotten cousin in the renewable energy family. Often there are lots of reports that come out, but many of them ignore biomass altogether, or bioenergy, and often it's considered sort of off the edge. But it's an important industry, and it's probably the oldest one of the oldest renewables we've got. And of course, we've got industries like the pulp Australian paper in Maryvale, producing something like 70 or 80% of their energy from biomass. And the pulp and paper industry is one of the biggest users of bioenergy. So biomass includes renewable organic material, so that's why it's effectively carbon neutral, from agricultural crops and forests, as well as the waste streams, municipal and commercial streams. Current installed capacity of bioenergy across Australia is around 812 megawatts, and but that represents only 0.9% of our total energy mix. So the Clean Energy Finance Corporation did a study a couple of years ago and compared Australia with the rest of the world, or the OECD, and said, well, we've got potential to increase that from 0.9% to 2.4%, effectively doubling our bioenergy capacity. And this would mean that we need between 3.5 and $5 billion investment by 2020. So that's an opportunity. And down there, you can see the mix. Most of our bioenergy at the moment comes from basically the sugar industry in Queensland. Has the biggest bioenergy facility, 65 megawatts there, running on bagasse, waste from the sugar production industry. And then you've got landfill gas plants collecting methane from landfill, turning that into electricity. And then you've got forest residues going into sawmills and to run their processes. And of course the pulp and paper industry. So types of biomass include, as mentioned, crop stubble, and forestry residues, wood processing residues. We've got quite a bit also from our food processing industry. Then you've got sewage, sludge, urban waste and commercial municipal waste. What we haven't got yet in Australia, but is an important industry overseas, many countries, is bioenergy specific plantings, short rotation crops grown specifically either for biofuel, liquid fuels that is, or electricity production. There's been a fair bit of work in this space already in Victoria and in neighbouring regions. In 2011, Regional Development Victoria ran the Victorian Biomass Audit, which I was part of that one as well. Got consultants to survey by ringing up people around the state and finding out how much material different industries had, organic material that could be potentially used for bioenergy. And that came out with a figure of 9.3 million tonnes per year, roughly. CSIRO's done a bit of work there too, as Paul's probably familiar with. There's the DAF Bioenergy Study, which was completed in 2011, which I was also part of. And that focused on two case study regions, one in Gippsland, prophetic I guess, and the other in Western New South Wales. For the Gippsland one, they found that there was between 0.75 and 1 million tonnes of biomass from the plantation industry there that could be used for electricity. And then in 2012, AMO contracted CSIRO to do an Australia-wide assessment of biomass from forestry, agriculture and cereals and grasses. This study this produced detailed maps. I don't think they've been made publicly available, but showing at a pixel scale where the biomass was being produced right across the country. And currently they estimate around 68 million tonnes of biomass, but as a result of expected increases in bioenergy plantings, estimated that would rise to 96 million tonnes by 2050, equivalent to 125 terawatt hours per year generation capacity. So there's reports if you want to look them up. So the recent study, as mentioned, was the ABBA project. This was funded by ARENA and RERDIC and government agencies around Australia, $6.2 million, surveyed the whole of Australia, and the purpose was to assist bioenergy project development and decision making to try and bring users of bioenergy with producers of biomass together, work out how you could bring the biomass streams together to make it more efficient and support local businesses get better value for their waste material. As Snow mentioned, the Victorian component was run by Sustainability Victoria, and I did that together with Arcadis. Was based on a mixture of survey this time and desktop modelling. And the results, the key output from this project is a detailed map right across Australia on the Renewable Energy website, which now includes, for the first time, biomass supplies at an LGA level. So it allows people to go in, see where biomass is, see where wind and solar are, and work out what the best options are for renewables in their region. And that's a website where you can find it. So some of the key results from the survey, altogether, similar to the previous study, about 9.7 million tonnes of biomass produced, and you can see the different sectors and how much is produced from each. The biggest one being grain production, a lot of stubble, technical term, shitload of stubble out there, which is, some of it's used for straw at the moment, but potentially you could use it for electricity production. The next biggest one, of course, is forestry. With this included forest residues, harvest residues from plantations, and sawmill residues. We excluded pulpwood, although that's been considered in other studies. Also excluded native forest residues, simply because they're a bit controversial to go and collect and burn. One thing the study didn't consider was existing markets and the economics. So it's purely the physical amount that could be removed, what we called sustainably, without depleting soil nutrients from the sites, and what was being produced by other industries. So, for instance, in the C&I, commercial industrial waste, that includes the brown component of that is paper and cardboard, which is used for recycling at the moment. So, 9.7 million tonnes of biomass. What does that mean in terms of energy? You can throw in a few assumptions and come out with about 11 terawatt hours per year of electricity being generated for Victoria. That translates to around a 1300 megawatt power station, or similar to Yallourn, or similar actually to what Hazelwood was producing when it shut down this year. And that's equivalent to 23% of Victoria's consumption. So biomass won't solve the whole problem, and of course these are overestimates, because when you factor in the economics it'll probably be considerably less, but there's a big potential to increase from whatever it is, not 0.9% at the moment. So the thing is, though, unlike brown coal, it's not in a convenient hole in the ground. It's spread right across the whole state. So it's not, you're not going to have a single 1300 megawatt power station. What it means is there'll be lots of distributed energy producers around regional centres if you go down this track. Some of the outputs from the project, this is the map of Victoria showing distribution of sawmill residues. I think this is wood chips or sawdust from sawmills actually. And straight away you can see how it shows up the hotspots where you might want to go and investigate a bit more detail. We covered the metro region as well, but that hasn't come out. You need to go in a bit closer to see that. And any of these LGAs, local government areas, you can click on, and it comes up with the details of the types of biomass there and the methodology used to estimate it. mentioned the ABBA study, I just wanted to also mention another study which we did a few years ago, which did actually look at the economic feasibility rather than just the physical amounts out there, the economics of putting in bioenergy plants. And this one focused on 2 case study regions, Mount Gambier in South Australia, centre of the plantation growing area of the Green Triangle, and Warwick Johnston in northern Victoria, centre of a cereal production region. I did this with Luis Rodriguez from CSIRO and a few other good friends there. And we looked at the costs of that biomass, getting that, growing it, harvesting it, transporting it to the centre. So how much would it cost to get the different types of biomass in? And from that we're able to come out with a supply cost curve for biomass material for that region. And you can see there, sawmill residues, the cheapest, they're already located in the town centre, so you don't have to transport them very far, and there's not much value in sawdust at the moment. Agricultural residues a bit more expensive because you've got competing markets there and further distances to transport them, and most expensive is when you get up into the hardwood pulp logs because they've got existing markets, so you've got to compete straight away with that. But when we did the modelling to look at, okay, how much would this mean in terms of electricity cost? For the lowest cost residues, sawmill residues, came out to about 5.8 cents per kilowatt hour, which is about $58 per megawatt hour. At the time of writing the report, said, well, this is much good because coal comes out at 3.1 to 4 cents per kilowatt hour, so it's 45% more expensive. But now with changing electricity prices, maybe it is a bit more attractive. But that was before factoring in REX. And of course, once you factor in renewable energy price, when we did this paper it was $34 per megawatt hour. It's bounced around a bit since then. The bioenergy plant was economic size. You could get your biomass for $46 or less per tonne. And in the Green Triangle region, there was about 69,000 tonnes, enough to power a 10 megawatt power station. So not a huge amount, enough for a small scale facility at that price. So what it did show though was that bioenergy was economically feasible in some regional centres, provided there was a concentration of biomass waste in that area. Of course, you've got a whole heap of uncertainties thrown in on this. We're not sure really how much harvest residues you can get from plantations. There's only been one real study looking at softwood plantations in Australia and nothing on hardwood plantations at all. So it's a potential for some movement in that area. Also, short rotation crops and bioenergy plantations. We can model their growth, but we haven't got anything out there. So not much learning by doing going on there at the moment. And then you've got the economics, competing markets, technological improvements, changes in electricity prices and changes in the REX price. And we've got the graphs there of the STC spot price and the LGC, large generation capacity spot prices up to today. So in conclusion, the studies been involved in show that there's around 10 million tonnes per year of biomass that's physically available across Victoria. However, only a fraction of this is likely to be economically available because of competing markets and uses, and the costs of harvesting and transporting the material. For a REX price of $34 per megawatt hour, bioenergy is cost effective, provided you can get that biomass for less than $46 per tonne. So there is potential for bioenergy plants in regional centres producing distributed energy, especially at the ends of those networks where you're likely to suffer from brownouts. And finally, going back to the recent study, the ABBA results provide a useful resource for people to go to look at opportunities for developing biomass projects, and hopefully it'll help bioenergy being accepted a bit more into the renewable energy family in the future. Thank you.
Thank you, Barry. Could I ask all the panellists to grab a seat and turn your mic on? We have a good panel session here. Do we have any questions for any of the panellists? Yeah. David, coming.
Thank you. This is a... Is that turned on? Yeah. I guess a postscript to Barry's presentation, and I must confess a certain, not conflict of interest, but personal interest in it, because the Division of Energy Technology some years ago developed the direct injection carbon engine technology, or at least built on what had been done at Man and in America. Barry was talking about efficiencies of biomass of 20 to 22 or 25%. The direct injection engine actually has, this is a modified diesel engine, is one of the most efficient ways of converting the energy in the carbon source into through power into electricity. We're talking about efficiencies approaching, well, for a modern diesel engine, 56%. Our estimate is for an engine fired with a biomass fuel about 47, 48, 49%. That actually doubles the amount of energy available, pretty much, that could come from this sort of technology. And we're also looking at short rotation crops, so not waste, which has been the focus of Barry's work, but in fact growing plantations. And in that context, there is actually two companies right now that produce 600,000 tonnes per annum on a sustainable basis, which could in fact supply 1 gigawatt of power once that engine technology is developed. And the engine is actually running at Newcastle right now. Well, it was recently, I don't know if it is today. So that's just a bit of a comment on that sort of technology. I think there's great potential for it in Victoria and elsewhere.
Yeah, thanks for that, David. I agree. I guess the thing with the new technological developments is there's always a bit of a lag with take-up and demonstrating the pilot plants and things, and also the specific requirements of the types of biomass. Biomass is a huge, a broad church, as you might say, for ranging from sewage sludge at one end up to high-quality pulp logs at the other end. But so you need to be careful what sort of material is actually suitable for your plant there. But yeah, if you can increase the, certainly there's potential to increase the recovery of energy from the 25% I was talking about there up to 30 or 40%, and that'll make a huge impact in the economics.
Yes, Michael, way over there.
Hello, Michael Barrie from the Melbourne Energy Institute. Keith, you showed that lovely graph with the different bits that made up the LCOE of a plant as you had more and more storage. I know some people looking at fancy new ways of power that don't operate on steam, like supercritical carbon dioxide and other things, which would make that concentrator cost, the heliostat cost, smaller because the plant efficiency would be higher. Do you have a sense of what kinds of further costs and LCOE reductions might be achieved by using alternative working fluids to steam and fancier generating plant?
Right. The supercritical CO2 is certainly one to watch. That seems to be well regarded around the world as a way to go, and it offers potentially higher conversion efficiencies, but also at smaller scales. And they're claiming that maybe they can do that at 10 megawatts or so at high efficiencies. And I believe they're talking about cycle efficiencies of around 50%. So it's very significant. Yeah. I think it gets you to the sort of cycle efficiencies you might get from combined cycle gas, but in a smaller, more modular thing at a lower temperature.
John.
For the three of you, we've been putting up figures of the levelised cost or whatever it is. I think the reality is there are some plants that are really well located, got lots of wind, lots of sun, close to a transmission line. They're pretty cheap. There are others that are not quite as well located. You've got to spend more on a transmission line, etc., etc. So the cost for each of those sort of things is there are some that are cheap, there are some, and so the story goes. And so I think that sort of says you'll get a graduated bringing of these plants in rather than everybody rushes in, bang, bang.
Comments?
Can I respond to that first? You're absolutely right, and if the market's working efficiently, then the best projects should get away earliest. And I think what we've seen in the wind space in Victoria is that the projects with the best combination of resource and access to transmission have got away now, but as the cost curve has come down, that's made a whole lot of other projects more prospective as well. And one of the things the larger turbines are doing is being more efficient at lower wind speeds. So you are opening up other parts of the state to development for wind, which were perhaps not so accessible when we had lower height turbines.
On the solar one, let's make a couple of comments. One is in terms of the resource. I mean, you can see which are the sunniest parts of this country and which are less sunny, and the land areas, I sort of don't even bother discussing it because we've got so much land, even in Victoria, that we could do all of our NEM generation several times over in northern Victoria, I think. So we don't have to sort of compromise on the quality of the solar in that sense. Back when we did our 2012 study of solar thermal potential, we estimated that you could put in about 15 gigawatts of capacity across the NEM, generating capacity, without having to upgrade or extend transmission. So that was a big start. Now I imagine, essentially what I'm saying there is common to large-scale PV. So large-scale PV is starting to take some of that, but the country's got a long way to go before we're limited by connection points. But at some point we will have to think about dedicated transmission investments. But as I see it, if those investments are used efficiently, they might represent maybe 10% or less of your total LCOE at the end. So I don't think in solar that you've got quite that sort of supply curve type effect really appearing. I think it's pretty much there for the taking.
The opportunity cost of land. I was chewing up some good. That's going to cost me a bit.
Well, that might be a question for Barrie here. I mean, the best place for solar is in a desert somewhere, so...
It's all in the desert, I've got no problem.
Don, you know Mildura the same way as I know Mildura. I don't think
Yeah.
you have to go far to find some very low rainfall country that wouldn't pay a lot for.
Yeah.
Bruce.
Bruce Godfrey from the Academy. Rachel, I'm just curious, as a wind farm developer and operator, what do you guys see as the best alternatives for firming wind, given that that wind's this horrible, nasty variable stuff, just like PV, then just terrible, according to a whole bunch of politicians?
That's a great question. I'm not sure that anyone's got the definitive answer to that, because there's going to be a price answer and there's going to be a technological answer. I think today the best firming alternative for wind is just to plug it into the grid. We have this incredibly diverse range of resource all generating into the same grid, and at the moment it actually works. 28 September notwithstanding, and that was not the fault of the wind farms. So that I think is the answer today, and I think we're actually all on a big journey to try and figure out what is going to be the most effective firming. And there are lots of wind farm developers who are now installing solar on the same site. That's not actually going to firm it, but it's going to do a different thing to the generation profile. So there's also going to be steps along the way. So we're not necessarily going to arrive immediately at a solution where every wind farm can react like an open cycle gas turbine.
But are you concerned that you're going to get forced into firming much earlier than you otherwise would have?
Yeah, I'm a bit concerned about that. I'm a bit concerned about how the generator reliability obligations are going to be designed, for example, and the way the state governments with their schemes are now requiring expressions of interest that include batteries, for example. That's probably a technological answer, but is it the economic answer? I'm not sure.
Hope you probably hear me. I had a question for Rachel as well, which is, thank you. I mean, we're hearing a lot today, and there's a lot of other people in the room who could probably talk about, flash new technologies and what the opportunity is. David's talked about DICE, for example. And the thing that always interests me is, what's the commercialisation pathway? You've got a bunch of investors who've had quite a rocky ride in Australia. They've had some good times, some bad times, and now good times again, I hope. So what's your view on the best way to improve, what would really improve that pathway for you and your investors for some of these newer technologies to become possible to start deploying them at scale and get onto that learning curve?
You mean for us to start deploying new
Yeah,
technologies? Well, I think some of the things Keith talked about are important. I don't entirely agree that we're lacking a time of day signal, because as you and I were discussing, that the energy price does that at the moment. But some kind of price signal or market mechanism that provides a value for having capacity sitting there that can be called upon, I suspect, is part of it. But otherwise, it's also wanting to see those technologies come down the cost curve a bit. Some of them, we're trying to drag them in perhaps a little ahead of their time. And I'm not sure what the answer is there. But in terms of strictly commercial investors wanting to make a return on their wind farm, asking them to suddenly bolt on a battery, I don't think is actually a very attractive idea for them.
Hey, the chair's prerogative. Question for a neophyte in our energy systems here is, what is the best way? You've got three very much, they're not niche, but they will be geographical in some ways. And you can bolt on a few other things there. So is it more economically desirable to have a national grid that somehow, rather than putting regulations on each one of you to have some storage, actually has the storage in the national grid? Is it more economically efficient to do that rather than ask all of you to do things which is probably not your specialty, and for you all to be independent rather than be part of a bigger grid?
If I could have a go, notwithstanding the details of what I might suggest about time of day signals, what I'm really trying to say there is, let's have a rational market signal, and I'm not a market expert, so I'm not really the one to design it, but it does seem wrong to sort of, and there seems to be a danger with this generator reliability obligation that it might get defined quite specifically, and someone's going to say, you wind farm, you must have an X. And as soon as you define it, it's almost inevitably going to be perverse if there's any danger of that. So if we have a market signal that allows people, there's a range of things we want in the system. If they have a market value that changes and the people who provide them get the benefit of that, and it's designed right, that seems to be how it should be.
Thank you. Question over here, and then we come back to David.
Just one thing, Snow.
Oh, sorry, Claudia.
Yeah.
Sorry, I don't want to kind of... we could get into a very esoteric policy discussion, but I do have form on this stuff. I mean, both Rachel and Keith are right, and certainly I would like to reassure people that the intention of the Finkel panel, at least, was not that the reliability obligation would be fixed and that it would be prescriptive. In fact, the idea is precisely the opposite, that what would happen is that the market operator would assess whether there's a deficit of reliability for whatever reason in a region, and then think about, well, if you're going to add a new generator to the system, will that make it worse? And in that case, you need to take steps at least to keep us on a level playing field there. And what would those steps be? Well, that's up to you. You can contract with an open cycle gas turbine or whatever to deliver that extra firming, and the amount of firming would be determined dynamically, so it wouldn't be you've got to cover your whole thing. So it's quite complicated as a concept, and to be honest, the best outcome would be that there's enough reliability in the system that we don't need to go down that path. But that's the intention of it. And that really, I think, demonstrates why I was making a bit of a face when Keith was talking about having a multiplier in the renewable energy target or whatever comes next for time of day, because what you end up with is a very blunt instrument that's fixed it's not dynamic, and both the size of the multiplier and the time at which it's applied very quickly become out of step, and you just lock in another perverse thing that doesn't work and rewards something that hasn't happened. And, you know, the RET's had an unhappy history with multipliers, as those of you who have paddled in that pond would know on the small scale. So it just doesn't seem the best solution. I think what's really important is we have this enormous opportunity now with the connectivity and the data to be able to have instruments that are much, much more responsive to what's really happening. And then, of course, the challenge for investors is to be able to say, well, when we look at that, what's that going to mean to the economics of whatever it is I'm going to put my money into? So the more dynamic the market is, I guess, the more tricky that is. But on the other hand, at least it means it's properly tuned, so you don't get this kind of rush to one side of the boat because a very prescriptive instrument's been put in place that's actually solving yesterday's problem. And certainly, I just would like to reassure people that the approach that was being recommended in Finkel was not to do that. And I don't think, with the work that AEMO is doing and the expert panel that I'm chairing, we'll certainly be very alert to that in the way that some of these things are going to be, the design proposition is going to be developed.
Thank you. Question over here.
So I'm afraid I have a comment on the generator reliability obligation. My name's Jill Caney. I'm from S&C Electric, and I'm an expert in that flash new technology of energy storage. And I guess I just wanted to comment that energy storage will not deploy unless you give it an income stream, which means there has to be a system service that is technically needed before it will arrive. So there is no point asking renewable generators to bolt on a bit of battery storage. It would be much better to have that as a service that a third party deploys that then generators can buy if needed. Yeah.
So we're saying that the generators could contract precisely for that. Exactly.
Thank you. A couple of quick questions. First Tony and then one to David too.
It seems to me, as the world gets more simple, it gets more complicated. And, you know, when you look at these things we're worrying about, I mean, the days when big spinning turbines just about did everything you wanted, you didn't even know you were getting half of them, seem to have gone. And now we're worried about, do we value those services as someone has to pay for them, or do we impose a cost on the absence of those services? In some ways, it's a bit like, you know, do you put a value on lower emissions, or do you put a cost on higher emissions? And so do you create markets for all these things? So we'll have hundreds of different sub-markets in the NIM, and so that's great for AEMO because they'll have lots of things to do. Or do you regulate some of those specific requirements? And that's where they're the choices I think we're faced with, because the issue is the same. The only question is what's the most efficient way to do this? And you know, it's quite clear that there is a higher value on dispatchable power than there is on non-dispatchable power. But how you secure that, most people would say, well, you're better off getting a market rather than a regulation. But it clearly is, it's a question more of, I suppose, on who is liable for that obligation. Is it on the system, or is it on the supplier who turns up with that particular characteristic? I've come to the conclusion it probably is on the supplier. Others will have a quite different view.
Thank you. Any comments from the panel? Well, David, we'll give you the last word.
Just a very quick one for Rachel. Can you comment on what the wind energy industry sees as the future trajectory for RECs and how low they might go? Because I'm really intrigued by the fact that 2 or 3 contracts, Origin and AGL, have both entered into agreements recently for power purchase agreements with wind farms for $60 or thereabouts a megawatt, in fact in one case below $60, which is bundled in with the RECs. Now the RECs at the moment are $85 a megawatt hour. They might have been 35 a few years ago. They're 85 now. That means that, what are they, Gold Wind or Wind Gold or whatever, they're actually giving away power and giving away money to Origin. And that doesn't quite make sense to me unless they're believing that the RECs will go to very low value in future years.
Good question. Just as there's a spot and a long-term market for energy, there's a spot and a long-term market for RECs. So what you're talking about in terms of $85 today is the spot price. The energy spot price today in Victoria is about $100. So if you're looking at $60 for a bundled megawatt hour of energy plus a REC, you're getting one of them free. Whether you're getting the REC free or the electrons free, take your pick. So this, this in both the energy and the REC market, this shows a disconnect between the immediate supply-demand imbalance, which is what's driving the high spot price, and then the longer-term market where those companies who've got the credit and the balance sheet, like Origin and AGL, to actually underwrite a long-term PPA, can get their energy and their LGCs or their REC supplied to them at the long-run marginal cost, which is got nothing to do with today's spot price, really. So you're not really comparing apples with apples when you look at the PPA prices that Origin and AGL are signing and what today's spot energy or REC price is doing.
Thank you. Look, can you join with me and thank the panel? They've done a great job.